So I will talk about the efforts that we are carrying of doing of porting the pixel tracking that of the CMS experiment at the HLT on GPUs starting from 2019. I mean the run 3 upgrade. So I will give you a brief introduction about the event selection strategy of CMS. It's 2 stages. There is a low-level trigger, which is reducing the input rate from 40 megahertz to 1 kilohertz, and this amount is such that can be stored, reconstructed. And we have a high-level trigger. I should have updated this number. It's 28,000 Xeon cores, because this 28,000 is giving you, by doing the math, if you do 100 kilohertz on 28,000, is giving you the maximum latency, the maximum average processing time that you can afford in order not to suffer by back pressure. That will be then 280 milliseconds. So you can also see in this slide how the average processing time is increasing, which is not increasing linearly, but quadratically with against the pileup. And if we take a look at the distribution in of the events, of the event processing time, we see 2 behaviors. One, which is a quick response. Basically, we accept the level 1 decision. The second one is a tail when we start doing the track reconstruction, and this tail can go on up to 3 seconds, basically. So this makes you feel that it's impossible to do to run pixel tracking and full track reconstruction for every event at the high-level trigger. So the idea, so we are talking about basically this upgrade, the long upgrade, and we are targeting this run 3. So the idea is behind online pixel tracking is to do fast tracking and vertexing using the information coming from the pixel detector. This is what we do online. Offline, instead, pixel tracks are used as a seed for a Kalman filter in the outer tracker. We just upgraded the pixel detector, so you see an X-ray representation. So basically, compared to the current is the past, and the upgrade is the current. Basically, this is the 2016 detector, and this is what we have now. We have 4 layers compared to 3 1 in the barrel, and we see 3 forward disks against 2. So the idea was, instead of just extending the pixel tracking, to write a new one and start thinking about parallel architectures. So tracking at the HLT during phase 0 is iterative. So at the first step, we do pixel tracks. They were done using triplets. Today, we do that. We do them using quadruplets. These are seeds for iter 0, which is targeting prompt high PT tracks. Then you have iter 1, which is targeting low PT, low momentum tracks, and then you have some recovery, which was using doublets, and today it's using triplets. Now, the problem is that evaluating pixel tracks is a combinatorial problem, and the entire HLT farm could have been dominated. The timing of the HLT farm could have been dominated by tracking. So we cannot rely anymore on the exponential growth of memory, which is guaranteed by manufacturers. So for this reason, both hardware and algorithm solutions have been studied. So the idea of the Patatrack project that we formed is that you have input events, 100 kilohertz of events, and you add a layer which is running pixel tracking for every event, but really fast, high throughput pixel tracking. So the objective is to create an application which takes raw data coming from the detector and gives tracks as an output, just like if we had a tracker that instead of giving you pixel data was giving you directly tracks. So the GPU memory transfers are hidden exploiting instruction level parallelism, and the ingredients for this are massively parallelism within the event. So we parallelize within the event. We have to develop software, which is algorithms which are parallelizable. Avoid useless data transfers and transformations, so we don't want at each step from raw data to digitized data to clustering. We don't want to send back data to the CPU, and renovation at algorithmic level. So if we wanted, actually we did, to extend the previous algorithm. So the previous algorithm consisted in create doublets, which are compatible with the beanspot, with the region hypothesis. Then propagate the doublet to the third layer. You find some hits. You connect them, and you have a triplet. This is the 2016 algorithm. Then, if you want to extend this, then you have all the triplets, and you propagate to the fourth layer. So you store quadruplets, and you start from another layer pair, and continue until you are happy. But this is not giving the impression of being a massively parallel computation. So this is not very suitable for GPUs because you don't see massive parallelism. You have very pure data locality. There are synchronizations which are due to the fact that first you have to do all the doublets, then you have to extend triplets, and so on. This is a very sparse and dynamic problem, but actually all the tracking is like this, and we are not going to solve this soon. But also, parallelization does not mean making a sequential algorithm running parallel. It really requires a deep understanding of the problem, and you want to renovate at the algorithmic level. So the idea was to rewrite completely the seeding code, and we created a graph which is also using the cellular automata paradigm. So basically, we take all the layers at the same time, and instead of propagating doublets, we take all the possible doublets at the same time, and we study this graph. So this is massively parallel because we can assign each thread, each CUDA thread, to a doublet. You have 500,000 of them, of doublets. And then you check compatibility between two doublets. And this can be done in parallel for all the doublets, for all the layer pairs at the same time. So you start building graphs of layers and possible layer pairs. And you assign each of these to a streaming multiprocessor of a GPU, which contains hundreds of CUDA cores. Sorry. So you can run this in parallel. It's a very massively parallel problem. And you use the cellular automata paradigm because you don't want to keep, in the end, all the possible seeds, doublets, triplets that you have produced, but you want to keep all the quadruplets. So you consider, for example, this quadruplet. You start from the innermost. If at the beginning all the states are 0, if this cell has an outer neighbor with the same state, so this will be 0 as well at the beginning, its state will be increased by 1. So if you keep going on, in the end, you will get quadruplets in the innermost layer pair, which have a state of 2. So this will mean that you can just consider those and run a depth first search to find all the possible quadruplets. If you are interested in pentuplets, you look for cells with a state of 3 and so on. Now, there is a problem with the integration. So today what we have is, imagine here you have the detector, you have the CMS front-end readout units, data are going in builder units, which are collecting events and then dispatching them to filter units for the reconstruction. So there are different possibilities. One is to have GPU filter units, but I mean, you have 8,000 nodes. You don't want to have GPUs in each of these nodes. This does not scale. So the other possibility, this is more for the long-term future, is to change completely the paradigm of computing farms and go to heterogeneous computing farms in which you have builder units and filter units, and then you have some racks of accelerators. They may be GPUs, they may be FPGA, TensorFlow, processor, TPUs, whatever. And on demand, builder units can ask GPU pixel tracker to run tracking, or filter units can ask on demand GPU pixel trackers to run tracking, and this is expandable. It's really easy to balance. If you need more GPUs, you just need another server. But it requires more communication and software development from the framework point of view. The other possibility that we also explored, and that I'm going to show in this presentation, is the GPU builder units. You have a small amount of these builder units, and you use them for reconstructing pixel tracks for every event. This is fast, independent on the filter unit development, and this is integrated in the readout. But this is requiring specific DAQ software development, because GPUs are seen as a detector. Okay, so going to the tests, some physics. So you have in blue the triplet propagation algorithm, in red the cellular automaton, the new one, and in black the 2016 HLT pixel tracking. You have the efficiency against PT. You can see that the efficiency is much better due to the new detector. The two algorithms are comparable, although in the very low PT the cellular automaton is behaving better. And this is the fake rate, and you can see that the fake rate for the cellular automaton is up to 40% lower than the triplet propagation, and cannot be compared at all with 2016 tracking, because you have more pure collections, because these are quadruplets and not triplets. Now going to the hardware. Now we acquired a machine, 2 sockets, Intel Xeon. You have 12 physical cores per socket, 256 gigabytes of memory, 8 NVIDIA GPUs, 1080 Titanium. The total cost is 5 bananas. We run a rate test. A rate test consists in preloading the host memory with few hundreds events. Then you assign a host thread to a host core. So in this case, you will have 20 and something host threads. Then you will have a host thread assigned also to a single GPU. You pre-allocate memory on the GPU, because you don't want to allocate memory for every event. And you start filling a TBB concurrent queue with event indices. So during the test, when a thread is idle, is stealing something from the queue. So it tries to pop from the queue a new event index. So in this moment, if the thread is associated to the GPU, data is copied to the GPU, and the GPU protests the events and copy back the results. Otherwise, if it is on the GPU, the same algorithm will run on the CPU, but of course without any copy. The tests run continuously for approximately 1 hour, and at the end of the test, we measured the number of events processed. So this is what happened in 10 milliseconds on 8 GPUs. So here you have 1, 2, 3, 4, 5, 6, 7, 8. There are, here you can see, so I'm colorblind, so I cannot tell you what kind of color is this. But this is, these are mem copies. These are the different kernels, and you can see that up to 8 kernels can run on each GPU at the same time. So rate test. At the end of the test, at the end of the hour of test, we measured how many events we processed on each core. So these are the 8 GPUs. These are the 24 CPUs going to bananas. So the total rate measured was for 8 GPUs, 6 kilohertz, 25 CPUs processed with a total rate of 600 hertz. So if you want to compute the number of nodes to reach 100 kilohertz is about 14, because you process is a hybrid CPU plus GPUs, and the total price for these 14 nodes is 70 bananas. So when running only with CPUs, the total rate is higher than here because they don't have to manage the GPUs. The total number of nodes to reach 100 kilohertz is 128. The nodes cost less, cost half. The total price is 320 bananas. And the energy efficiency, so energy powered was measured during the test. The 8 GPUs together were burning 1 kilowatt. So this means 6.3 events per joule in total and 0.8 events per joule per GPU. Instead, okay, the CPUs were using the same amount of power when running in hybrid or CPU only, and they were using, processing 3.2 events per joule in a hybrid mode. Since the rate is higher in CPU only, you have 4.05 events per joule. So this means that if you build 14 of these, and I don't remember the number, 128 for the CPU only, in the end you get less amount of power needed, which is, again, less bananas. So going to the conclusion. So the pixel track signaling algorithm has been completely redesigned. This is already running on CPUs in our software framework, and this is giving exactly the same bit-by-bit results on the GPUs, which will make the going to this paradigm much easier because you don't have to demonstrate that you have better or worse physics performance. So this will allow us to do better physics because you can run tracking for every event instead of 10% of the event. And we started to port also more expensive part, other expensive part like the reconstruction of the multi-fit of the calorimeter. So last thing, the CA algorithm will add graph knowledge, and this makes tracking completely new and more powerful tool. So we will make this more flexible by also steal some work from the Kalman filter. Thanks. That's it.
How did you arrive at your banana estimation for the CPU only versus the GPU only? Because on the face of it, the GPU server with 8 GPUs inside would cost.
I mean, the conversion is, I get the price.
So this is actual prices.
Yes.
Not estimated.
Yeah.
All right.
No, it's not estimated. It's what we paid.
Impressive.
Did you make some estimation using KNL or just ZONs?
No, not yet. I mean, it's the same algorithm. It's running TBB on the CPU, so it can run on a KNL. But no, because I don't have money to buy a KNL today. Banana, sorry.
A quick question. So these are gaming GPUs, huh?
Yep.
I mean, the bananas look so favorable because these are gaming GPUs to the extent.
Yes.
Are you not worried online running gaming GPUs? They're not making 24/7. I mean, because gamers normally don't last that long.
It depends because from what I have been said, so 14 nodes are a low number. are too low for the AQ. I mean, if you want to bring the entire data from the detector.
BUs in CMS. Yeah, you need about 70, 74 or something.
Sorry? What?
You need more. Yeah,
you need more.
You need more.
So in theory, you can have, instead of 8 GPUs, you can add 1 or 2 more powerful in per event builder and have more and something like this.
Is your algorithm running single precision rather than double?
But it is also offline. I mean, it's also offline. In the offline reconstruction, we run single precision. We are not losing precision because it's never running double precision.
I just wondered because the GPUs for gaming are very low on double precision performance.
Okay, and let's take it for the coffee break. Sorry, because we are running.
There is no coffee break.
There's no more coffee break. Well, yeah, between the there's no more coffee break actually, but there's a photo at 10 to 7. I take the opportunity to remind you. 10 to 7, we have to be outside and we leave for the photo.